Welcome back. Today we're going to tackle a really cool physics problem from I.E. Irodov's legendary problem book. It's a classic cyclist's dilemma. Imagine you're on a track where the grip changes depending on how close you are to the center. To go faster, should you take a tighter turn where the grip is strong or a wider one where it's weaker? We're going to use some straightforward physics and a little bit of calculus to find that perfect path. But the goal here isn't just about getting the right answer for this one cyclist. What we're really doing is building a problem-solving blueprint, a method that you can use for all kinds of tricky physics questions. So let's break it down step by step.
Okay, first things first. Let's get a really clear picture of what's going on. We've got a cyclist, sure, but the track they're on is, well, it's pretty unusual.
So here's the kicker. The grip, the friction, isn't constant. It actually changes based on the radius r. Look at that formula. At the dead center of the track, where r is 0, the friction coefficient k is at its absolute maximum, k0. But as the cyclist moves outward toward the edge, the friction gets weaker and weaker, dropping all the way to 0 at the outer rim. And that sets up our whole puzzle, right? A tighter circle needs more force to make the turn, but it offers more grip. A wider circle is a gentler turn, but you have less grip to work with. Our job is to find that perfect sweet spot, the one radius that gives us the best possible balance for the highest speed. Whenever you see something moving in a circle, your first thought should always be about forces. So, we gotta ask the most basic question here. What force is actually keeping our cyclist from just skidding off in a straight line? And that force is the centripetal force. It's the center-seeking force. Now, this is a really important point. Centripetal force isn't some new magical force that just appears. It's always the net result of other real physical forces, like the tension in a rope swinging a ball, or gravity keeping a planet in orbit, or, in our case, the friction between the bike's tires and the track. And this is the classic formula that connects everything. It's the bridge between the forces and the motion. It tells us that the mass of the cyclist, their speed, and the radius of their turn are all related to the amount of inward force needed to stay on that path. The faster you want to go, or the tighter you want to turn, the more centripetal force you're going to need. It's as simple as that. So let's think about it. Is there a rope pulling the cyclist? Nope. Is it gravity? Well, gravity is just pulling them down into the plane, not sideways. The only force that's actually pointing towards the center of the circle, preventing the bike's tires from sliding out, has to be static friction. Static friction is the hero of our story here. It's the grip. But, and this is a huge but, it has a limit. A really common pitfall is forgetting this. You can't get infinite friction. If the cyclist pushes it too hard, tries to go too fast, or turn too sharply, the centripetal force they need will be greater than the maximum friction the track can give, and that's when they start to slide. Okay, so this equation right here, this is basically the heart of the whole problem. The maximum available friction force is the coefficient k times the normal force n. Now, since the cyclist is on a totally flat horizontal plane, the upward push from the ground, the normal force, is just perfectly balancing their downward weight. So we can just say n equals mg. Then all we do is plug in that special radius-dependent formula for k, and we've got our expression for the maximum available grip. All right, so we've got our two key pieces. We have an expression for the centripetal force we need, and we have an expression for the friction force we have. Now we can put them together and build one single formula that describes the cyclist's speed. And this is how we translate the physics into math. To hit that absolute top speed, the cyclist has to be right on the edge, pushing the friction to its absolute limit. That tipping point right before the tires would slip is where the required centripetal force is perfectly equal to the maximum available friction. So we set them equal. And notice something really cool that happens? The mass m is on both sides, so it just cancels out. That tells us our final answer isn't going to depend on how heavy the cyclist is at all. Pretty neat. And boom, here it is. This is our master equation. It's a fantastic relationship because it tells us the maximum possible speed, well, speed squared, for any circle of radius r the cyclist decides to ride on. But we don't want the speed for just any radius, right? We want the speed for the best radius. So we've built this awesome formula that links velocity to the radius. Now our mission is to find that one specific value of r that makes v as big as it can possibly be. If you actually plotted this equation out with velocity on the y-axis and radius on the x-axis, you'd get something that looks like a hill. It would start at 0, rise up to a peak, and then fall back down. We are looking for the very top of that hill. And luckily for us, math has the perfect tool for finding the peak of any function.
Yep, it's calculus. The derivative tells us the slope of our function at any given point. So if we set that derivative to 0, we're essentially asking the question, at what point does the slope of our hill become perfectly flat? And that point, of course, has to be the very top. Now here's a quick pro tip. It's way easier to find the maximum of v squared than v itself. And since v is always positive, they're both going to hit their maximum at the exact same radius r. So let's make our lives easier.
So when we do the math, when we take the derivative with respect to r, that k0 and g are just constants, so they hang out in front, the derivative of r is just 1, and the derivative of r squared over r is 2r over r. Now, we know k0 and g aren't 0, so the only way for this whole thing to equal 0 is if that part in the parentheses equals 0. And just like that, we've done all the heavy lifting. We turned the physics into math, and we used calculus to pinpoint the optimal condition. So now we can finally reveal the answer for the perfect path and the absolute top speed our cyclist can hit. The equation 1 minus 2r over r equals 0 solves to r equals r over 2. That's it. That's the answer. The optimal radius, the one single path that allows for the absolute maximum velocity, is exactly half of the total radius of the plane. It's such a clean, elegant result. So for our last trick, we just take this perfect radius, r over 2, and plug it back into that velocity equation we derived a few minutes ago. A little bit of algebra later, and there it is. The fastest possible speed depends on k0, that base friction value, g, the acceleration due to gravity, and r, the size of the track. Okay, so we got the answer, which is great. But honestly, the most valuable thing we've built here isn't the solution itself. It's the process we use to get there. This method can be your blueprint for a huge range of mechanics problems that you're going to face. I mean, just look at this blueprint. We followed these exact 6 steps. We deconstructed the problem, we identified the forces, we applied our core physics principles, we built a mathematical model, we optimized it using a derivative, and then we solved for the final answer. This kind of systematic approach can turn a really scary problem into just a series of logical, manageable steps. And this is so, so important. As you work on your own problem sets, try to always focus on this. Understanding the why behind every step is what builds real, lasting physics intuition. Look, memorizing formulas will only get you so far, but mastering the process, that's a skill you'll have forever. Seriously, think about it for a second. What about finding the perfect angle to launch a projectile for maximum range? Or figuring out the most stable orbit for a satellite when its thrusters are firing? This method, modeling a system and then optimizing it, is one of the most powerful tools in all of physics. What will you solve with it? Thanks for joining us.